Today we're going to cover Chapter 4, Section 2, Second Derivative and Graphs. In Section 4.1, we learned about the first derivative and what it can do. Now we're going to learn about the second derivative and what it can do. So concavity talks about, is it increasing or decreasing? So when it looks like this, where it increases, that's concave up. Where it goes up and then goes down, that's decreasing, that's concave down. So concave up, concave down. Second derivative will help us understand where the graph is concave up, where the graph is concave down. So concave up, the slope of the tangent at A is less than the slope of the tangent at B when A is less than B. For concave down, the slope of the tangent at A is greater than the slope of the tangent at B whenever A is less than B. Slope of the tangent line is decreasing and the graph is below each tangent line. The graph of the function f is concave up on the interval AB if the first derivative is increasing on AB. The graph of the function is concave down on the interval AB if the first derivative is decreasing on AB. Geometrically, the graph is concave up on AB if it lies above its tangent line in AB. The graph is concave down in AB if it lies below its tangent line in AB. So to take the second derivative, you basically take the first derivative and then take the derivative again. Notice that first derivative is 1 prime, which looks like 1 apostrophe. Second derivative is 2 prime, looks like 2 apostrophes. So if I had the function x cubed, the first derivative would be 3x squared. The second derivative would be 6x. You simply take the derivative twice. Take the derivative twice. So if I was looking at the graph of x cubed, you notice that the graph of x cubed starts with concave down and goes to concave up. So if you look at the second derivative, it will tell us where the graph is concave down and where the graph is concave up. And notice that it changes at 0. So less than 0, it's concave down. After 0, it's concave up. We can see all that with the second derivative. So we take the first derivative of x cubed, that's 3x squared. We take the second derivative, that's 6x. And we can see before 0, it's concave down. After 0, it's concave up. So if we work on the example cube root of x, x to the 1/3. Let's back up just a second and focus more on this. Let's go to our calculators. And if we look at f of x equals x cubed, okay, to talk about when the graph is concave up, when the graph is concave down, we first take the second derivative. First derivative is 3x squared. Second derivative is 6x. Now, what we will be talking about, and I'll go ahead and introduce now, is called the inflection point. The inflection point changes from concave up to concave down or vice versa. How do you find where that change happens? You take the second derivative, set it equal to 0, and solve. So we have a possible inflection point at 0. Remember, to find out where that point is, we plug it into the original. 0 cubed is also 0. So we have an inflection point at 0, 0. But to verify that, we want to go ahead and look. So we go to my calculator. We'll go to y equals. In y1, we'll put x raised to the 3rd. We'll do zoom 6 to do a standard window. And then if I want to look particularly at 0, 0, I can hit second trace, 1 for value. Type in 0, where we found. And we can see that's where the change happens from concave down to concave up. Now, how can I know that it's concave up or concave down? Well, we can make a sign chart for that. So if I make a sign chart, the number that we're concerned about is 0. We got 0 by taking the second derivative, set it equal to 0 and solve. Now we're going to look at what happens to the second derivative before 0 and what happens to the second derivative after 0. So I go to my calculator, I type in 6x, which is the second derivative. When I go to the table and plug in numbers before 0, you'll notice that all the results are negative. That tells me we're in a concave down area. If I plug in numbers after 0, you notice that all the results are positive. That tells me we are in a concave up area. And again, all of this can be verified if we graph the original in an appropriate window. We can see 0, 0 is the inflection point where it changes from concave up to concave down, or vice versa. In this case, concave down to concave up. And we can see before 0, concave down, after 0, concave up, and the sign chart helps verify that. We plug into the second derivative. Okay? So let's say we had the function cube root of x, which can be rewritten first as x to the 1/3. The first derivative will be 1/3 x to the negative 2/3. I wouldn't simplify it at that point. I'd leave it because we know we're going to take the second derivative, which will end up being 2/9 x to the negative 5/3. So we have our second derivative, and we're graphing the original derivative. And let's go ahead and see when is it concave up, when is it concave down. Okay? So again, our original is x to the 1/3. We're going to take the second derivative to find concave up or concave down. So the first derivative is 1/3 x to the negative 2/3. Take the second derivative, 2 primes. That would be negative 2/9 x to the negative 5/3. And if I want to find the inflection point, again, we take the second derivative, which I'll go ahead and simplify, negative 2/9 x to the 5/3 equal to 0. Okay, so to find the inflection point, it's where it's equal, set the second derivative equal to 0. Now in this case, when I try to solve, let's say I do 0/1, and I cross multiply, we get 9x to the 5/3 times 0, which is 0. X is gone. 0 doesn't equal negative 2. That's not true. There is no solution. So the inflection point could be, we have to go look, excuse me, where we take the second derivative set equal to 0, or where the second derivative is undefined. So basically, there's no solution here. So let's go look at the graph. Let's go look at the graph and see what we have. But we do know that it's undefined if we plug in 0 for x. So again, there may be no solution, but it's undefined. If I plug in 0, you can't divide by 0, it's undefined. We know that at 0. So let's go ahead and go to the calculator. We graph the original, x raised to the 1/3. Graph, we're keeping the window of 10 by 10 by 10. And we found that at 0, it's where it's undefined. Slope is undefined. But if we look at it before 0, it's concave up. After 0, it's concave down. So that's where the change happens. That's where the change happens, is at 0, but it's undefined there. And if I take the second derivative, let's use a sign chart. Again, 0 is where we're seeing the change happen. And we go to the second derivative. Let's plug in numbers before 0 and after 0. So the second derivative, we can type negative 2 divided by 9x raised. Actually, be safe. Let's put all that in parentheses. Good practice. Negative 2 divided by parentheses 9x raised to the 5/3. And if I plug in numbers negative 1, negative 2, negative 3, negative 4, negative 5, all the results are negative. In the second derivative, that's where it's concave down. And if I plug in positive numbers, numbers after 0, notice all of those are negative. So one more time. Make sure it's in the screen. If I plug in negative values, all of those are positive. positive, sorry about that. So that area is concave up, and then everything after 0 is concave down because all the numbers are negative. So to verify that at the graph, if we graph the original, go back to the calculator, graph the original x raised to the 1/3. 0 is where the change happens. Before 0, it's concave up. After 0, concave down. The sign chart verifies it, where I take numbers before 0 into the second derivative, we get positive results. Concave up, concave up. After 0, our results are negative, all negative, so we get concave down. Okay. So, kind of reviewing the 4.1, if you plug into the second derivative and you get positives, you're in a concave up. Why? Because if you plug into the first derivative, they'd all be increasing. If you plug into the second derivative and your results are negative, that means you're in a concave down area. And if you plug into the first derivative, that's where it's decreasing. So there's a relationship between first derivative and second derivative. But remember, first derivative is defined increasing or decreasing, where the original graph is increasing or decreasing. Second derivative is defined where the original graph is concave up or concave down. Okay, so if we have the graph of e to the x, let's talk about that one. Well, the first derivative of e to the x is e to the x, and then the second derivative would be e to the x. And if we graph e to the x, notice that e to the x is concave up the entire portion, the domain is all reals. So if I do the sign chart for that, I go to my calculator. The second derivative is e to the x. And the entire, if I put in negatives, let's say -3, -2, -1, 0, 1, 2, 3. It is positive. It is positive on all numbers. So anytime I plug in a number like -3 all the way to 3, my results are positive into the second derivative. It's concave up for all of it. So it's a nice way to check. And we can always graph it. Go to y equals, type in e to the x, hit graph. I have it in the normal window still. And you'll see that it's concave up the entire way. Now, if I had ln of x, and I took the second derivative, let's go ahead and work that out. So if I had ln of x, remember from previous sections, the first derivative of ln of x is 1 over x. And then to take the second derivative, I'd rewrite that as x to the -1. So the second derivative will be -1 x to the -2. The second derivative would be -1 over x squared. So we need to know our derivatives. Okay, so we're graphing the original ln of x, and we're going to find out where it's concave up or concave down using the second derivative. So I go to my calculator, and let's graph ln of x. We'll use the same normal window, but you'll notice something interesting about ln of x. ln of x only exists from 0 forward. So the numbers we'll plug in are from 0 forward, but it's concave down the entire way. So again, we can use a sign chart to verify. Remember, we're plugging in the original. It's all about the original, but for the sign chart, we're looking at the second derivative. So I go to my calculator. The second derivative is -1 divided by x squared. And then I go to the table and notice that negative, there's an error at 0. Remember, we're only talking about the positive ones, so it's when it's greater than 0. And you notice that all the values are negative. Therefore, the entire graph is concave down. Okay, so again, bottom line, how do you find where the graph is concave up or concave down? You take the second derivative to find where the change happens. Take the second derivative where it equals 0 over where the second derivative is undefined. And we use a sign chart to verify, but we graph the original to see what's going on. We graph the original to see what's going on. So an inflection point is a point of the graph where it changes from concave up to concave down. We take the second derivative. We can see where that happens. It's kind of like the critical point we talked about before. An inflection point, we set it equal to 0. Let's take the second derivative, take it to 0, or see where it's undefined. Make a sign chart. I like to graph the original. We'll do both. Okay? So what we're going to do is we're going to review 4.1 and 4.2 all at the same time. We're going to review 4.1 and 4.2 all at the same time. Okay? So let's start with reviewing 4.1, and then we'll add 4.2. So here's our original function, 4x to the third plus 6x squared minus 72x minus 30. Okay? So there's our original function. And in 4.1, we want to find where the graph is increasing, decreasing, but also find those maxes and mins, those local max, local mins. So let's start with that. Now, the way we do it is we take the first derivative, set equal to 0 and solve, check where the first derivative is undefined, and if we had any endpoints, which we don't, that would be the domain, we would also check that. So basically, first step, take the derivative, 12x squared plus 12x minus 72. Okay, so to find the local max, local min, where it's increasing, decreasing, all that's with the first derivative. And the three things we want to get in the habit of checking is one, we take the first derivative equal to 0, and then solve. Well, you got to know your factoring. We can factor out of 12, which gives us x squared plus x minus 6. Then we can factor x squared plus x minus 6 would be x and x. This would be plus 3 minus 2. Then we set each piece, so the x equal to 0, x plus 3 equals 0, x minus 2 equal to 0. We get two possible extrema, local max, local mins, at x equals -3, x equals 2. The other thing we need to check is we look at the derivative, first derivative, and see if there's any place there a number that we can plug in to be undefined. Since we're not dividing by x, there's no dividing going on at all. There's no numbers that would make it undefined. And then the third thing we checked, if we have any endpoints, that would be a domain that hasn't been incorporated yet. No domain, no endpoints, none. Okay, so to figure out what's going on at -3 and 2, we make a table. We're going to look at -3 and we're going to look at 2. But please remember, first we're going to go look at the graph, then we'll make a sign chart. So first, let's look at the graph. I take those points and plug it into the original. Remember, all of this is about the original. All of this is about the original. We use the derivatives to find information about the original, but it's all about the original. So I go to y equals, I type in the original, 4x raised to the third plus 6x squared minus 72x minus 30. Okay? I go to the table feature. The numbers I'm concerned with are -3 and 2. Okay? So the points where there could be possible extrema, possible maxes or mins, are at -3, 132, and 2, -118. Now there's two ways to verify if those are maxes or mins, local max, local min, and that's to graph it and the sign chart. We're going to do both. I prefer the graph, so you can see the actual graph of what's going on there. Sign chart is going to help verify. So the downside is we need to make sure we can graph this thing to see it. Looking at the x's, we need to go from -3 to 2. So I make a comfortable window, maybe from -10 to 10. Again, you can make it shorter, maybe -5 to 5. That would cover the -3 to 2. As long as you got those points covered, we don't want to start at -3 and 2 and cut those points. We want to have a little cushion. And then looking at the y's, 132 and -118, we're going to have to go maybe down to -150 to cover those. -150 all the way to 150. maybe counting by 50s. Then maybe from negative 10 to 10, counting by 2s. Okay, so the downside is you have to make a window to see it. But the good news is once you see it, if I went from negative 10 to 10, counting by 2s, I press window, go from negative 10 to 10, counting by 2s. My y, I'm going from negative 150 to 150, counting by 50s. Again, graphing the original. You can see it go up, you can see it go down, you can see what's going on there. Then if I hit second trace, 1 for value, if you look at negative 3, there we have a local max. Y to the left and to the right are lower, therefore we have a local max. If I type in 2, that's down here, to the left and right are higher, therefore we have a local min. So looking at the original graph, negative 3, 132, and 2, negative 118, let's get your quick graph, you can see we have a local max, and we have a local min. Okay, that's by graphing the original. That's the way I prefer, but the sign chart will also be helpful. So with the sign chart, the two numbers that we're looking at are negative 3 and 2. And if we're looking for local maxes and mins increasing, decreasing, we're plugging into the first derivative. So I go to my calculator, go to y equals, type in the first derivative, 12x squared plus 12x minus 72. Go to the table, plug in numbers before negative 3, so negative 4, negative 5, negative 6, negative 7. All of those are positive. And in the first derivative, that means it's increasing. Excuse me, plug in numbers between negative 3 and 2, like negative 2, negative 1, 0, 1. All of those numbers are negative into the first derivative. That means it's where the graph is decreasing. So if it's increasing then decreasing, that's why we have a local max there. If I plug in numbers after 2, like 3, 4, 5, 6, notice all of those are positive. That's where the graph is increasing. So if we're going from decreasing to increasing, 2 would be a local min. Okay, that's all review from 4.1. Now what we're focusing on is 4.2. So in 4.2, we're looking for where the graph is concave up and where the graph is concave down. And then we do that by finding the inflection point. So for the new section, 4.2, we don't take the first derivative, we take the second derivative. So the first derivative is 12x squared plus 6x minus 72. The second derivative is 24x plus 6. Okay? So for that, excuse me, we're going to first find the inflection point. How do we do that? We take the second derivative, set equal to 0, and solve. Subtract 6. Oops, sorry, that's 12x. The first derivative is 12x squared plus 12x minus 72. And then our second derivative would be 24x plus 12. Sorry about that. 24x squared, 24x plus 12. Okay, so double check your derivatives. So the second derivative is 24x plus 12. So we take 24x plus 12, set equal to 0, subtract 12, 24x equals negative 12, divide by 24, divide by 24, x equals negative 1/2. Okay, we have a possible inflection point at negative 1/2. And remember, to find out where that is, we plug it into the original. Okay, so go to y equals, type in the original, carefully watch out for mistakes. Okay, so we plug in the original, go to the table, type in our inflection point, negative 1/2. We get negative 1/2, 7. So that's a possible inflection point at negative 1/2, 7. But how do I know if it is or not? We have to check it. So we've already have a good window. We graph the original. Graph goes up, graph goes down. And remember, an inflection point is where it changes from concave up to concave down. So if I hit second trace, value, negative 1/2, At negative a half and a 7, that is where the change happens. It goes up, down, it's concave, down. Then it changes at negative a half 7 to concave up. That's where the change happens. So now you have the original, you can say before negative a half, it's concave down. After negative a half, it's concave up. But we can verify all that with the sign chart. So again, remember, our second derivative is 24x plus 12. The number that we found is negative a half. So with the sign chart, we're going to look at before negative a half and after negative a half into the second derivative. So if I go to the second derivative and type in 24x plus 12, put the second derivative in, go to the table feature. Remember, before negative a half would be like negative 4, negative 3, negative 2, negative 1, all of which are negative. That's where it's concave down. Numbers after negative a half, like 0, 1, 2, 3, 4, are all positives. That's where it's concave up. So at negative a half, that's where it changes from concave down to concave up. So we have an inflection point. That's where the change happens. An inflection point at negative a half, 7. And we can say that it's concave down from negative infinity to negative a half. Or we can say when x is less than negative a half. And it's concave up from negative a half to infinity, or when x is greater than negative a half. And that is section 4.2. That's the main part of section 4.2. So, again, take the second derivative, set equal to 0, solve, you get that negative a half, you can make the sign chart, and you can verify with the original graph that there's an inflection point changing from concave down to concave up. And if I just give you a graph, you can see by looking at the graph that we have a local min at negative 1, 0. We have a local max at, let's say, 1 and 3, 1, 3. You can see that there's an inflection point where it changes from concave up to concave down somewhere, like that 1.5, 0. And we have x-intercepts at negative 1, 0 and 2, 0. So if we just have the graph, you can see everything. That's why my main message is to graph the original, and you can see it all. We can see where the graph is decreasing. We have a local min at x equals negative 1. You can see where the graph is increasing. Below the inflection point. See where the graph is increasing, decreasing, and all by looking at the original. And if we graph the original and the derivative, you can see the changes happening through this graph. Okay, so when we're doing curve sketching, we want to analyze the graph, find the domain, the x-intercepts, y-intercepts, analyze your first derivative to find the inflection points where it's increasing, decreasing. Look at the second derivative to find concave up, concave down, and inflection points. And then we can summarize everything. So let's do one big summary of everything we've learned in this chapter. So if we had x cubed minus 3x squared, if I had the function x cubed minus 3x squared and I want to analyze the graph, the very first thing we're going to do is find the intercepts. Okay? So remember, to find the intercepts, if you want to find the x-intercept, you make y0. If you want to find the y-intercept, you make x0. So you remember all that from algebra, and it's all about the original. So to find the x-intercept, we make y0. So x cubed minus 3x squared, set that equals 0. Factor out the x squared, x squared times x minus 3. X squared equals 0, x equals 0, x minus 3 equals 0. we get x equals 3. So we find that we have an x-intercept at 0, 0, remember it's a point 0, 0, and at 3, 0. So we find that we have two x-intercepts at 0, 0, and 3, 0. To find a y-intercept, we make x 0. So this is our graph. Our function is x cubed minus 3x squared. If I make x 0, you get 0. So we have a y-intercept at 0, 0. So the first thing we do is find the intercepts. To find the x-intercept, make y 0, solve. So we have two x-intercepts, 0, 0, 3, 0. To find the y-intercept, we make x 0, and we get a y-intercept at 0, 0. Okay? Second thing we're going to find is to find the extrema. Now, to find the extrema, we take the first derivative. So our original function is x cubed minus 3x squared. We take the first derivative, we get 3x squared. We get 3x squared minus 6x. Okay? And then we're going to set that equal to 0. Remember the three things we look for? We look for extrema. We take the derivative. First derivative, set it equal to 0. I can factor out a 3x, we get x minus 2. Set each piece equal to 0. X equals 0. X equals 2. Okay. Now, the other things we want to check, look at the first derivative. Is there any place where it's undefined, divided by x? None. And then we also want to check if there's any endpoints. That would be a domain that's given first, and they didn't give us any of those. So the 2 points we're concerned with to find possible extrema, possible highs and lows are 0 and 2. So we make a table, 0 and 2. Remember, we plug it into the original. We plug it into the original. Okay? The original is x cubed minus 3x squared. Plug in 0, plug in 2, and we get the points. So remember the original is x cubed minus 3x squared. X cubed minus 3x squared. So we plug in 0, we get 0. Plug in 2, we get negative 4. Now we need to find out, do we have a local max or local min there? Well, first, let's graph the original. So to graph the original, we need an appropriate window. For x, we need to see 0 and 2, so maybe go from negative 5 to 10. For y, we need to see 0 and 4, so maybe go from negative 10 to 10. And maybe just do the whole thing, negative 10 to 10, all the way around. Because remember, the goal is to see 0, 0, and 2, negative 4. So we've got a window, negative 10 to 10, counting by ones. Negative 10 to 10, counting by ones. We see our original graph going up and going down. So it goes up, down, up again. And at 0, 0, and at 2, negative 4, we can see what's going on. So if I go to my graph, second trace, number 1 for value 0. At 0, 0, we have a local max. To left and right or lower, we have a local max. And at 2, negative 4, left and right or higher, we have a local min. Okay? That would be using the graph, which is what I prefer, but we can also do the sign chart. With the sign chart, the numbers we're concerned with are 0 and 2. We plug into the first derivative. So I go to my calculator. The first derivative is 3x squared minus 6x. Numbers before 0, like negative 1, negative 2, negative 3, all of those are positive. That's where the graph is increasing. Numbers between 0 and 2, like 0.5, 1, 1.5, 1.75. All of those are negative. And then the first derivative, that's where the graph is decreasing. So again, increasing and decreasing, we have a local max. After 2, like 3, 4, 5, 6, all those numbers are positive. That's where the graph is increasing. So decreasing, increasing, that's where we have a local min. So the sign chart verifies that we have a local max at 0, 0 and a local min at 2, -4. That is review for 4.1. Now, the third section is 4.2. So 4.2, we have the original, which is 3x to the third minus 3x squared. But the new stuff, what we're doing now in 4.2, we take the second derivative. So the first derivative is 3x squared minus 6x. The second derivative is 6x minus 6. And again, to find the inflection point, we take the second derivative, say equals 0, add 6, 6x equals 6, divided by 6, divided by 6, x equals 1. So we have a possible inflection point of 1. Again, let's first graph and see what we have. We take the 1, plug it into the original. So I go to y equals, type in the original, x raised to the third minus 3x squared. Go to the table, type in 1, and we get 1, -2. So we believe we have an inflection point at 1, -2. But let's see it. Let's go look at the graph, and we've already graphed it. So I'm going to hit graph. We already have it in a window. And we can see the graph being concave up, and then it goes to concave down. So if I hit second trace, 1 for value, 1 is what we found. You can see that's where the change happens from concave down to concave up. So yes, that's where we have an inflection point. And we can verify it with the sign chart. So with the sign chart, the number we're concerned with is 1. Plugging into the second derivative. So I go to my graph, I move my y equals, type in 6x minus 6. And if I plug in numbers before 1, like -2, -3, 0, -1, all of those are negative. That's where the graph is concave down. After 1, like 2, 3, 4, 5, 6, all those numbers are positive. That's where the graph is concave up. So the change from concave down to concave up, which is what we saw in the graph. So that's 4.2. So in summary, what did we find when we analyzed the graph? We found that we have 2 x-intercepts at 0, 0, and 3, 0. We found that we have a y-intercept at 0, 0. We found that we have a local max at 0, 0. We found that we have a local min at 2, -4. And we found we have an inflection point at 1, -2. And we know it's concave down from -infinity to 1, or when x is less than 1. And it's concave up from 1 to infinity, which is when x is greater than 1. And that's what we're learning up to 4.1 and 4.2. Notes. It walks you right through the steps. Step 1, find the x-intercept and y-intercept. Step 2, using the sign chart, finding that we have a local max and a local min. And then step 3, taking the second derivative, finding the inflection point, finding out where it's concave down and concave up. All leading with the sign chart where it's concave down, where it's concave up, and the inflection point. We can sketch it, and we have our summary while looking at the original graph.